Hi everyone, my name is Lana. I am a fifth-year PhD student in the Processor Architecture Lab, and today I will talk about my research on high-level synthesis. High-level synthesis, or HLS tools, take high-level software code, for instance C or C++, and automatically produce the corresponding hardware design. The idea of HLS is to enable not only hardware, but also software developers to build efficient circuits, and of course to increase designer productivity. HLS tools are used by many companies to program FPGAs, but they still face some challenges. Firstly, they are primarily suited for hardware designers, which understand the underlying hardware and know how to tune and refactor the code to get good performance. And secondly, they are good for regular applications, for a certain type of applications, but when it comes to general purpose control-dominated code, they usually do not deliver the highest possible performance. So today I will discuss some of the limitations of standard HLS, and then I will talk about a different way to do HLS that I have developed during my PhD. So what does a standard HLS tool do? It takes a piece of code, for instance, the loop that we have here, and then it produces a data path of components that implement the functionality that we want, as well as a controller, which dictates when each of these operations will be triggered. The idea, of course, is to create the best possible schedule, to use the data path in the best possible way, for which we would use techniques such as pipelining. The idea of pipelining is to overlap loop iterations as much as possible to increase the throughput of the design. So in this case, by looking at the code, we can see that loop iterations are completely independent, which means that we can start a new loop iteration on every clock cycle. We see here that we are doing a read cycle by cycle, we are starting a new multiplication, and eventually we are adding up all of the results. So this is great when compile time information is sufficient to build such a schedule. But unfortunately, this is not always the case. Let's take a look at this example. Here, we are reading a value of x. We are using this value to address array of hist. We are doing some computation and then storing back to memory. Now, depending on the values of x, there may or they may not be read after write dependencies between consecutive loop iterations. In our example, between the second and the third iteration, there is a read after write dependence because we are reading the same value that we have stored in the previous loop iteration. So we do not know at compile time where these dependencies exist because we do not know the values of x. So what a standard HLS tool would do, it would build a conservative schedule where it assumes that there is always a read after write dependence, and each load will be scheduled for after the previous store completes. So this ensures that if there actually is a dependence, it will be correctly honored because the load happens after the store in every case. Of course, this results in low performance, and what we would like to do is something like the schedule below. Here, loop iterations that are independent are perfectly pipelined, and only when a dependency actually exists are we postponing the load for when the previous store completes. And this is the type of behavior that we would like to achieve. So to achieve this, we have developed a new HLS strategy. Instead of using a compile time controller which decides exactly when each operation will execute, we build Dataflow circuits which have a distributed control mechanism. All the components communicate with handshake signals, and they decide locally as the circuit runs when the data will be exchanged between components. So basically when all memory and control dependencies are resolved, data will be sent from one component to another. There is no predetermined compile time schedule, but we will dynamically schedule as the circuit actually executes. Now this is the circuit, Dataflow circuit, that implements the loop that we have seen before. So all of the operations inside our loop body will be translated into the corresponding Dataflow components. And the loop itself will be implemented using a merge and a branch node. A merge node will take a value either from one predecessor or from the other, depending on the control flow. So in this case, it will take either the initial value of the iterator or the previous one coming from the branch. And the branch is the one that decides when to terminate the loop. It will compare the loop iterator with a loop bound and then decide whether to exit the loop or to send data back through the merge to start a new loop iteration. Like any standard synchronous circuit, we will use buffers which serve as registers, and then we will use forks which replicate a piece of data to send to multiple successor components. Okay, so let's see what is the behavior of this circuit. Data will enter through the merge and into the buffer, and now from the buffer it will be sent into the data path to all successors. It will also be sent through the branch, back through the loop, and into the buffer itself, which will start a new loop iteration. So once this happens, we are able to start a new loop iteration because we have new data in our buffer. But now we have a problem. The adder here has only one of its inputs available. Of course, it needs to have two to start performing the addition. So it will tell the load that it is not ready to take this data at this point of time. The load, in turn, tells the fork that it cannot receive new data because it already holds data from the previous iteration. And the same thing will happen here with the store. The store has only one of its inputs available, so it will create a stall on the load, which will again tell the fork not to send new data forward. So this means that our data here will stay stuck inside the buffer until the data from the previous iterations is sent to the successors in the data path. And this means that although we have dynamic behavior, we cannot achieve high performance that we want. There are some slow paths that are causing back pressure and preventing us from pipelining our loop. So to resolve this issue, we have developed a strategy to place and size FIFOs into the design to relieve back pressure in the slow paths and to allow fast paths to propagate data at a high rate. In this particular example, even though these components will be creating stalls, the FIFOs will accumulate the data coming from the buffer, which means the buffer can issue data through the branch and into the merge at a high rate, therefore achieving high parallelism. So now we can achieve the schedule that we see here. We are starting a new loop iteration on every clock cycle by sending data through the branch into the merge at a high rate. But there is one issue which we have not resolved yet, and those are the read after write dependencies. So far, there is nothing in our design to ensure that whenever a read after write dependency exists, it is actually honored. We see here that the load is actually executing before the store to the same address, which would give us an incorrect result. So this is our same circuit. All of the loads and stores connect to memory, and those that are potentially dependent are the load and the store to array hist. So for these accesses, we will build a specialized component called the load store queue, just like a processor implements. And the role of this load store queue is to ensure that those accesses that are dependent are executed in the correct order. So even though the load store queue may receive accesses out of order, for instance, we may receive 2 loads before we get a store from the previous iteration, the load store queue will check which addresses they target and ensure that those that are dependent are happening in the correct order. For instance, if this load and the store are targeting independent addresses, the load can go ahead before the store. But if they are dependent, the load will have to wait until the store. And this finally gives us the schedule that we wanted to achieve, where independent loop iterations are perfectly pipelined, but those that have a dependency are the load is postponed or after the store. And this behavior is not possible with standard techniques, and it is similar to that achievable in out-of-order processors. Of course, there is more that we can do that standard HLS cannot. Our ability to create dynamically scheduled circuits allows us to incorporate speculation in our designs. The idea of speculation is to issue some pieces of data before we are certain whether they are correct or required. So we will have components called speculators. This can either be a branch speculating on the branch condition or memory sending speculative loads, which will send speculative data to the rest of the components. Of course, we cannot have speculative data modifying memory or terminating the program. So we will add specialized units, which we call commit units, which let only correct data through, and that data that has been misspeculated will be discarded at these points. If we are discarding some computation, we also need to be able to replay computation. And we will do this using save units. The idea of save units is to save copies of all the data that passed through. And in case we need to replay, this data will then be reissued in the rest of the Dataflow design. This creates a speculative region which has a speculator. It is bound on one side with the save units and on the other side with the commit units. So to quickly show some results, we are comparing our designs, the square here, with statically scheduled standard HLS. We are looking at the normalized resources and performance of our designs compared to the static ones. We see that in all cases that have memory dependencies, control dependencies, or those that can benefit from speculation, we get significant performance improvements compared to static techniques. Okay, so to conclude, HLS is gaining importance, but current techniques are not sufficient to support general purpose applications that we are facing. It is important to look at new ways to do HLS, and I have discussed one of them today. All this work is available on our website, so you can check it out. And thanks for your attention. I hope to see you at EPFL in the fall. Bye.